Dennis emailed me Monday morning. And I did not have anything prepared, so this is kind of rough, although I've been talking about and thinking about this topic for a long time, as you will shortly see. So last time I was here, Python was a pretty cool language. I'm still shocked that we're now number 4 on the most conservative list of popular languages, and number 1 or 2 on other popularity ratings. And Dennis just asked me, how come Python is so popular? I don't actually know. I have a wild guess, which is that data science has lifted all boats. I don't do data science myself. I barely know what a pandas thing looks like. I'm sure several of you here spend a lot of time with that, so yay, Python. But as always, Python is easy to read, easy to learn, easy to write, but that comes last, actually. And I should actually call out my great mentor, Lambert Meertens, who in the late 70s, early 80s designed a language named ABC that was designed to be easy to read and write and learn, for which I was one of the 4 or so programmers tasked with implementing ABC. After 3 or 4 years, the project was canceled for lack of popularity, and Python is really just a remix of ABC, with perhaps the biggest difference being that ABC used capital letters for keywords, as was sort of prevailing fashion in the late 70s and before. Other things that sort of make Python a good thing for people, it lets you write short code, but not so short that it becomes cryptic. And it comes with batteries included. There is a huge standard library. Plus, it's really easy to put in different batteries, better batteries, batteries I had never heard of, batteries I don't care about in the form of third-party packages. And Python, as well as everything in Python's ecosystem pretty much, is open source, which makes my work easier because I don't actually have to do any of it anymore. I just have to say I'm the BDFL. Now, let's just do a quick poll. Who here is familiar with coding in Python from sort of regular? Okay, that's almost everyone, so I don't really have to explain too much about Python's runtime type system. One of the reasons that Python is concise is that you don't have to be explicit about the types of your variables, arguments, return types, and other things. Python does all its typing at runtime. So from a compiler's perspective, there's not much more you can say about a typical name that occurs in Python except that it is an object. This is true even if it's a very primitive type like integer or string or floating point number. There are no unboxed values in Python. There is some obscure library that will let you manipulate unboxed values, and in the data science world, NumPy arrays are actually arrays of unboxed values, but everything is sort of demarcated by APIs that mean that the type system of the language itself has no worries about unboxed values. It also has no opportunities for efficient code generation because the compiler just doesn't know. It's object-oriented. It supports multiple inheritance. If you really want to, you can do crazy things like write a function that computes a list of classes and use that as the set of base classes for your class. You can even create your own meta classes. I'm not going into too much detail here. As I mentioned, there are no declarations as such. Well, the only type of declaration is about the scope of a variable, but nothing about its type. You just say def add of a and b, return a plus b, and it either works or it doesn't when you call it. Also, and a lot of people don't appreciate this when they start using Python, variables are not actually really variables in the sense that they are in most other programming languages. In Python, a variable is basically just a dynamic binding. In most places, what the user thinks of as a variable and what the language actually goes to considerable length to make you believe is a variable is really just a key in a dictionary. And when you assign to that variable under the hood, it sets a value in that dictionary. This is also why the origin, at least, of why you can delete variables in Python. Now, for local variables in functions, there are certain constraints that make it possible for the compiler to actually cheat and not materialize that dictionary and, in fact, just manipulate values as if they were registers or something like that. But for the most part, you can't actually tell the difference. You have to sort of really try to use some introspection API before you can tell, oh, I guess in this context, there is no real dictionary. Or you have to read the reference manual. So, unlike some other dynamically typed languages, in Python, there is still a certain level of type safety which comes purely from the interpreter being fastidious in doing type checks when they matter. When you try to add two objects together, and one of those objects is an int and the other is a float, great. We'll turn the int into a float, add the two floats, and return the float. On the other hand, if one of them is an int and the other is a string, we'll throw a type error. Now, if you try to multiply an int and a string together, you probably know what happens. That's not a type error. You get a repeated string. Other things that are interesting in the type system that more or less follow from all this, the concept called duck typing, I guess the technical term would be structural type checking or structural subtyping. When you call a method on an object, it may or may not work. If it works, you win. If it doesn't work, well, you have a bug in your program. That's the sort of the attitude, which means that you can do all sorts of interesting things where you pass a function, an argument that has an attribute that is actually a method, and the function calls that method, and it will work for any class that defines that particular method. There is no requirement to say, well, the right method on files can be called here, but the right method on some other object cannot be called, even though it happens to be called right. Duck typing for the win. People love it with sort of some limitations. Also, with this dynamic type system comes a lot of introspection. If you want to know what the attributes of the data attributes of an object are, you can ask for that object's dunder dict attribute. We pronounce under as dunder. If you want to know what its type is, you can ask for its dunder class attribute. If you have a particular class and you want to check whether it's an instance of that class, you can call isInstance like in most languages. Then there are all sorts of interesting quirks where at some point we added an interesting new feature like decorators, context managers, descriptors, a whole bunch of stuff that is well defined but is not apparent from the syntax of the language, or only marginally so. So why do we like dynamic typing, or why do Python's users in general like dynamic typing? Well, less typing, finger typing means shorter code, less boring code. You can use those dynamic tricks to add a little touch of excitement, like if you have a function that takes arbitrary keyword arguments, then you can also turn those arbitrary keyword arguments into attributes of the current instance. Of any instance, in fact, although I wouldn't recommend it necessarily. Why does this not lead to terribly buggy programs? Because we also have a culture in the Python world of doing a lot of unit testing and other types of testing. I remember it's sort of settled now. I think PyTest has mostly won. But like a decade ago, there was a battle of different testing frameworks. And that was a good thing. There was lots of interesting developments were going on. And this was all open source stuff there where I didn't really have to do much. So dynamic typing is clearly popular. On the other hand, the static typing people have not given up yet. Static typing definitely catches bugs earlier, at least some bugs. It clearly doesn't catch all bugs. With static typing, you have a little more confidence when you're refactoring your code. If you add an extra argument to a method, then static typing will tell you when you forgot to add an extra value to a call site. In addition, and I call type declarations, I call them type annotations because that's what we call them in Python, now that we sort of have them. Human readers of large code bases, the people who sort of are hired to maintain 1 million lines of code that they didn't write, but they're still going to be responsible for fixing it or adding stuff to it. Those humans really appreciate having something that tells them what the types of arguments of functions are. And you can say, well, we have documentation. Well, documentation doesn't always stay up to date, sadly. I wish it was not so, but it turns out that it's really hard not to get the type annotations, keep the type annotations up to date, because the compiler will tell you when they don't match the code. And it turns out static typing is also still pretty popular. So there is this new concept. Well, it was new a decade ago, although I think I only heard about it about 4 years ago. Gradual typing. In Python, we typically call it optional static typing. It is a technique for adding static typing to a dynamic language that lets the user basically mix and match statically typed and dynamically typed parts of their code. Now, obviously, this means that if you want to cheat, you can just keep your code dynamic and the compiler will not catch you. We're not into that kind of bondage and discipline. You're just shooting yourself in the foot. But if you want to have more confidence about the correctness of your code, not perfect confidence, but some better confidence, if you want to benefit from some of the benefits of static typing, including its popularity, you can start using type annotations in your Python code now. And sort of we've developed this over the past half decade, and we found that it is actually a very reasonable way to introduce typing into a large dynamic code base. Python is not unique, of course. TypeScript is exactly the same idea for JavaScript, and Facebook did the same thing for PHP with hack. So mypy. I just noticed it's doubly open source. It's a type checker for Python. It was developed in, I think, starting in 2012 or so by a Finnish guy named Jukka Lättisalo. I can never pronounce his name. He got a PhD from Cambridge, England from that. Pretty good work. I remember he approached me at a Python conference either in late 2012 or early 2013, and he said, look, I have this language that is sort of inspired by Python, but I've added static typed annotations to it in a gradual fashion, because that was also part of it. And I've written a type checker and a transpiler that turns that code into Python code, which you can then execute. I said, wow, that's great. And how many users do you expect to have? Well, you know the story about the typical language developed by a PhD candidate. There's one user until the thesis has been approved, and then the number of users goes down to 0. I didn't come up with that story. That I heard that from someone in the Haskell world. Anyway, I said, but if you change your syntax just a little bit, let's start by turning the angular brackets into square brackets, because the angular brackets will not work. And we can change a few other things. And guess what? You can actually make your language a superset of Python, or maybe a subset. I'm never sure in which direction this goes. But you can make it compatible with Python so that you don't need the transpilation phase. Code written in language X, well, language mypy, is valid Python code and will execute, and the Python interpreter will execute it just fine. And in fact, the Python interpreter will execute it at the same speed as it would completely unannotated code. Well, Jukka thought about that, and together we sort of whipped up a plan. And after that, and after I hired him at Dropbox, we started actually introducing this in the Python community, and we started working on standardizing this. This happened in 2014, 2015, with a very contentious PEP 484 that takes existing function annotation syntax in Python and basically says, henceforth, function annotations will be used for type annotations. Because syntactically, these things already existed in Python. That was the sort of the hint I was giving Jukka. But semantically, there was never any agreement on what they meant. And sort of when we started the Python 3 work, there was also a very contentious discussion about adding typing to Python somehow. And after sort of going around that subject several times myself, I realized that we would never get agreement, at least not in time for Python 3.0, and probably not in time for Python 3.10. We would never get agreement on exactly how those type annotations should work. But I said, if we just add a little bit of syntax without giving it meaning, then people can experiment with assigning different meanings to that syntax. The big debate, by the way, was about whether these type annotations are just used for correctness checking or whether they're also used for runtime checking or possibly even for code generation. And it turns out that you need sort of quite different approaches for the different ideas, and I wasn't sure that I knew what I wanted, but I knew that eventually we would want some kind of type annotations. Well, so that happened. Because Yuka worked at Dropbox, he started sort of playing with mypy and the Dropbox code base during events called Hack Week. And in 2015, I think after the second Hack Week where we played with it, we started introducing annotations in the Dropbox code base for real. Fast forward to this year, we now have over 2 million annotated lines of code. Now, how do you count that? It means that the total line count of the functions that are annotated is about 2 million. This out of 5 or 6 million lines total. We currently have a 4-person team, including Yuka. It's pretty popular. In fact, we almost never hear anything negative about this except about the speed of the tooling or the speed of the introduction of type annotations in the remaining 4 million lines of code. We also, because mypy is open source and we kept it open source and we aggressively developed it open source, so all the design discussions about how should we solve this problem in mypy, the entire bug tracker, everything in all code reviews is done on GitHub. And as a result of that, we have quite a few external contributors, some of whom occasionally get promoted to core dev and sometimes to Dropboxer. We've also found that Facebook adopted this, Quora adopted this, Lyft adopted this. There is an open source chat bot named Zulip that is a Python code base of about 100,000 lines of code that was completely annotated over the course, I think, of the previous summer. So anyway, I think that's a pretty healthy project. The standardization effort also paid off because it's now supported by other type checkers for Python. Perhaps the most well-known of which is PyCharm, popular IDE, which has its own code completion and type checking engine, but which supports the same syntax that we introduced for mypy. Google has a static analysis tool that will eventually help them port their, I don't know, tens of millions of lines of Python 2 code to Python 3. Facebook was so excited that they wrote their own type checker, which they just recently open sourced at the last PyCon last month. And then there is a component which is sort of type stubs or descriptions of the standard library and third-party packages that haven't been annotated that everybody shares and contributes to. So with the project status out of the way, let's start showing some code and give some details. So an important requirement was that there would not be changes to the Python syntax, which is where the existing syntax for function annotations was essential, which is also why I convinced Yuka to change his angular brackets to square brackets, because it turns out that in Python you can overload array indexing or dictionary indexing on anything, including using meta classes on types themselves. So you can define the meaning of list square bracket int square bracket close as this refers to a list of integers. The other requirements were that Python itself should not slow down and should not actually do anything with the types. So you can put all the annotations you want in your code. your code executes exactly as if those annotations weren't there. And finally, no transpilers. Otherwise, we would have a lot more syntactic options, but it would also be incredibly hard to get people to adopt this, because transpilers only work if all the tooling understands the sort of the richer syntax that the transpiler accepts. And so I'm very happy that we didn't go that way. So now here's a tiny bit of code. I'm not using a fixed width font because I think that's old-fashioned for slides. Let's sum a thing named X, sorry, a thing named A. We start with a total initialized to 0. We loop over all the things in A, and we add those things to the total, and then we return the total. Well, you can see that if A was a list of integers, or a list of floating point numbers, or a list of, or maybe a NumPy array of complex numbers, it would all make total sense. There are also things where it doesn't make sense, but that's okay. Like, you can't sum a list of strings this way because the total is initialized to a number type. So this is fine. This is also still fine in mypy, but of course it's not type checked. Now let's add an annotation. So we add list square bracket of int square bracket close and arrow int to the function heading, the signature, and that's the only change we make. Now the mypy type checker has enough information to figure out what's going on, and it will in fact say this is fine, because I don't have any examples with bugs in them. So the syntax for annotations is name : type, where type can be anything that we'll explain soon. Return type is indicated using an arrow. I think there are a few other languages that use the same notation. It's definitely not very common. But Python is not unique. I don't know, maybe Python sort of inspired the other languages that they have this. I think Rust uses the same notation. And Scala also uses square brackets for generics. This same function, we could annotate it differently, for example, with list of floats to float. Now, if you're still a Python 2 user, this is the only slide I'll spend on the Python 2 syntax. There is a Python 2 version of this syntax which uses a comment that we call a type comment, bound type : and then in this case, types in parentheses and in arrow for the return type. Note that the type comment does not repeat the variable names, the argument names. Otherwise, this does exactly the same thing as the Python 3 version. In fact, you can write this even in Python 3. Why would we allow using type comments in Python 3? To enable people to write code that is Python version neutral, which is an incredibly important property of code while you're porting it to Python 3. Oh yeah, a reminder that we have about 1.5 years until Python 2 is officially unsupported, which doesn't mean that the world suddenly will stop using it. Okay, so how does type inferencing work? This may be fairly basic. A simple example, the sum of two integers. For some reason, I assign the sum to an intermediate local variable x, and then we return that. And how does the type checker go about sort of figuring out what's going on? Well, let's focus on the line x equals a plus b. So we start by looking up the types of a and b, which come from the signature. So we know that both a and b are ints. Then, because we have operator overloading, we're looking up the function dunder add on integers I'm simplifying things here. If you know how binary operators work in Python, you know it's much more complicated, but the complications don't add anything to explaining the type inference. So now we have this dunder_add method on the type of A, so that is actually int.dunder_add. Can it be called with an int? Darn tootin' it can. So what does it return in that case? Because that function could be overloaded. And in fact, I believe it is. Because if you call it with a float, it will magically also work and return a float. Yes. If you call it with an int, it returns an int. And that is the type assigned to the variable x. Well, on the next line, return x, we do a similar thing. We say, well, what is the type of x? Because that's the entire expression. It's int, because we just computed that on the previous line. Is that the desired return type for this function? Yes, bingo. Okay, the whole function works. There's a lot more to this. In particular, I'm not touching on the notion of context, where in some cases, if you have a variable whose type is declared, the declared type can actually influence how we interpret the types occurring in the expression that's being assigned to it. That seems overly complicated. It turns out it's essential to deal with all sorts of corner cases of Python. I don't have time to go more into that if I ever want to get to the end of this talk. So then we have the question, well, what can a type be? I've shown a few very simple examples, int, list of int. Well, there are only a very small number of atomic types. Others are string and bytes. Well, they're not even atomic, but they're sort of common built-in types. Then we have container types. And those are, in fact, not built in because, again, for obscure technical reasons, you have to spell them with a capital letter. At least that's how we made it so that you can use this in versions of Python that were already released before mypy was invented. So capital list with square brackets is a list of whatever occurs inside those square brackets. We also have sets. Dictionaries have two type parameters because, of course, there's a key type and a value type in Python, unlike some other languages where the key type is always string. Tuples are technically not generic types, but a special form. For example, a tuple square bracket int bool is a 3-tuple. There's also a way to spell a tuple of a variable length, but I don't really like those guys. Perhaps more useful than the concrete container types are the abstract container types like sequence and mapping and mutable sequence. There's at least a dozen of those. For those, the existing names already were predefined in Python's collections.abc module, which is pretty old. From the first time we introduced abstract base classes in Python. For mypy, we basically sort of steal those names and give them aggressively better meanings. Then there are a bunch of things that are not so regular. There is a type named any, which means, well, for this particular variable, don't bother checking the type because I'm going to do nasty things to it. Which perhaps you shouldn't do in a perfectly well-typed program, but in practice in Python and sort of on the path to gradual typing, realistically that happens. Also, Python has a bunch of dynamic features that when used sparingly are very useful. Then there is a whole bunch of stuff that I really don't want to get into much. There is optional, which says it's either an X or it's none. Very useful. A very, very common sort of style of using things in Python, even in untyped code. How often do you see if x is none? Then there is union, which is, well, it could you can say union of int and str. It could either be an integer or a string. Then you have to insert a runtime type check, just like you would do if the code was untyped. I'll get to those a little later. There is a callable type. You can say, well, the type must be none, which is not very useful for arguments, but pretty popular for return types, obviously. Then there's no return, which means this thing never returns. It either loops forever or it raises an exception. There's a couple of crazy things having to do with strings and bytes. And more things, name, tuple, type, dict, and new type that you can look up in the manual. So of course these types can be combined. Here is a very verbose function signature, sequence of tuple of float and float, returning tuple of float and float. We can solve that with a type alias, which is just a Python assignment that takes a type on the right, like tuple of float and float, and assigns it to a name on the left. And mypy is smart enough to realize, oh, this is not a regular variable assignment. This defines a type that I can then use later. And lo and behold, you can now write the signature using list of vec and vec. All pretty standard stuff. So escape hooks, already mentioned any a few times. There are other escape hooks. There's a cast. The cast is completely unsafe. Maybe at some point we should add a downcast to the repertoire, which actually checks that you're doing a downcast and not just casting to some random object, other type that's unrelated. But we currently don't have that. We do have a cast, which is like the last resort. MyPy is apparently confused about what the type of node is. We tell MyPy, don't worry, I know it's a list expression. And then you can use it as a list expression. There's also a different way to just suppress an error that MyPy might give. For example, if you import a module that MyPy cannot find, you can put a type ignore on that line, and then MyPy will not tell you that it cannot find it. However, it will create a variable, or at least in its own representation of your program, it will say, well, there is a variable named setup tools that has type any, and if you call a method on it, the return type is still any.
A question on
Sure.
So, how diverse is the heterogeneity of the implementations of Python? I mean, nobody makes 36-bit machines anymore, for instance, but there are non-byte oriented 64-bit machines, for instance.
I don't know that there are any Python implementations that run on such unusual platforms. CPython is portable as long as you have 8-bit bytes and your integers are at least 32 bits. And we're slowly entering a world where we're not even caring about, we don't even care about integers or pointers smaller than 64 bits. There are some other Python implementations, Jython, which runs on the JVM, IronPython, I think is still in existence, which runs it on Microsoft's DRL. I'm not sure what the cast sort of could do differently for other platforms. I mean, this cast is not there to truncate bits or anything. It's really there to correct the type checker. And the list expression example was actually meant to be downcast, but there's not much difference. Generics. Okay, so we have generics. I already showed list of int and dict of, well, here's a slightly more complicated dictionary that has string keys and tuples of 2 integers for values. You can also create generic type aliases. You need a type variable. Type variables are one of the warts of the type system because we didn't have a way to sort of introduce type variables without pre-declaring them. So you have to call a utility function to create a type variable. And you shouldn't be playing dynamic tricks with that because the type checker is not actually ever executing your code. The type checker is just reading your code and trying to guess what it means. Anyway, so we can create a generic type alias named pair, which is a tuple of 2 values that have the same type. And then we can derive from that a type alias named vec, which is a pair of floats. And then we can define the same add vectors function again. You can also define your own generic classes, which is much more interesting stuff than using them. Again, you have to start with a type variable. And then you start with a class statement, stack, class stack. Your base class must be generic of some type variable. Now you can also include other base classes still, so you can have multiple inheritance from a non-generic class or from a differently generic class. But basically you must have generic of t in there. Now we have an instance variable named data declared in the class using Python field 6 and later syntax. We spent a lot of time debating how we would introduce variable declarations that were somewhat similar to the function annotations that we already had, and we ended up introducing syntax that does not use a new keyword. You just say variable name : type. And that has worked out pretty well, very sort of short and Pythonic. Before that, you would have to use a type comment on a variable initializer. Anyway, this is your classic stack, except I forgot the full or empty method. There's a push that takes a t, there's a pop that returns a t. For things that return nothing, you have to explicitly say returns none. And then on the right, we create the stack. So to create the stack, to instantiate that generic class, you have to first instantiate stack of t to stack of int, and then you have to call that to create an instance. There's some caching there to make it fast. Now you push an integer, you can not push a string, at least. I mean, at runtime you can, but if the type checker catches you doing that, it will give you an error. You can pop something from that stack, and then the inferred type for that variable will certainly be in an integer, which you can prove to yourself by sort of trying to do something to it that you can't do with integers. There's also a built-in function only in mypy reveal type that will just print the type as an error message. That's really just for debugging. What are we getting to here? Runtime type checks. So say you have an optional, a function upper that takes an optional string, and apparently there are some cases where we want to be able to pass none into it, and then we want to get an empty string back. A different version actually would also return an optional string. But let's say we want to always return a string. So the way you write that is if the argument is actually a string, we call the upper method on it. There's an existing string method named upper, but of course you can't call that on none. Otherwise, if it's not a string, we just return an empty string. On the right is code that works the same way, except instead of using isInstance, it just checks if it's none, return an empty string. That's actually more idiomatic. MyPy understands both versions equally well. And it will understand that in one branch of the if statement, the type of the variable is actually stir. What do we have on the bottom? We have a similar case where we take an argument that could be any object, which you can express with object. And unlike any, object does not suppress any error messages. So you can't do anything with an object because the type checker says object has no methods. Well, you can convert it to a string, that's about it. So if that object is an integer, then we add 1 to it, and otherwise we just give up and return 0. On the right, I have a little helper function that takes an optional int and returns a non-optional int. And at runtime, it just throws an assertion error when the argument is not none. Oh, sorry, when the argument is none. Again, the type checker understands things like is instance or is none or even just false, sort of A equals B or just if A. It understands those things in assertions as well as in if statements, and it will do the right thing there. So that's, again, those 3 statements on the bottom right type check correctly. The require call will, in fact, raise an assertion error if there's no key in that dictionary D, which is apparently the functionality that we want for this particular require function. Yeah?
So that behavior of the type checker understanding his instance, is that encoded in some sort of specification, or is that just how mypy works and the user has to understand that? Like pyre might work differently, for example.
No, we have that particular one we have nailed down in PEP 484. Yeah, but PEP 484 does not nail down every corner case of the type system, unfortunately. And there are other corner cases of inference where it doesn't specify things completely. And unfortunately, pyre and mypy give vastly different answers on some programs, actually on many interesting programs. But mypy is sort of the reference implementation at this point, and the pyre people are feeding us sort of complaints and bug reports and feature requests. And I expect that they will also send us requests to change the standard. Let's see. So after PEP 484, good thing you mentioned that, we started sort of evolving the type system a bit. And probably the biggest addition is protocols or duck typing. I'll try to read through this example quickly. There's a log function that takes a message and a file object, and it appends a new line to the string argument and then writes that thing to the file. It's a very primitive logging function. Then there's a class save, which derives from the stack class I defined previously, just for convenience, and to show that you can inherit from a generic class, sort of specializing it to a specific type, because save is no longer generic. It is a stack of strings that has a write method. So the write method just pushes that message on the stack, and I don't know what happens to it after that. So we're creating one of those savers, and we try to log to it. Now, if you run that code, it will actually work. But if you try to type check it, you get a complaint from mypy saying, that save object, never mind that it has a write method and everything works just fine, it's not actually an instance of I/O of stir, which is the very elaborate type that defines the I/O streams in Python, which has like 24 methods, write and read line and read lines and read into and is a TTY, way too many methods. It's also generic because you have files of strings and files of bytes. Anyway, the type checking doesn't work well here. So we want a way to say, accept anything that has a write method. Well, actually, accept anything that has a write method that takes one argument that is a string. So here we go. We define a class writable, and we inherit it from a predefined thing named protocol. We add a method to it. The method is a complete dummy. There's a pass there. You can also literally use the syntax ... instead of the pass, although that won't work if you're also Python 2 compatible. This is not a class that you can instantiate. This is a class for putting in signatures. So now we change our log method, and the rest of the code is the same. We change it to say that the file argument is a writable. Well, since the only thing we do with it is call its write method, that works just fine. And since that save class actually has a write method of the correct signature, that last line, the log call, is actually now correct. And this is how we deal with duck typing. There are a few details, like in most versions of the typing module, you would have to import protocols from a typing extensions module, but we'll smoothen that out eventually. So the key thing to note here is that writable is not an abstract base class, because save does not, in fact, inherit from writable. So without protocols, you could only solve this by defining an abstract base class that defines the write method, and modifying the IO class, which is deep inside the standard library, to inherit from that writable class. We did this long ago in the standard library for one or two very popular duck type methods. Like there's a hashable class there, which if you check dynamically, is this thing hashable, you can use the isInstance blah of hashable, and the hashable class overloads the isInstance behavior and just checks, is there a write, is there a dunder hash method? That stuff doesn't really scale. Yes, question?
So does mypy understand classes that overload isInstance and is subclass?
That it does not. That is really difficult, because that mypy would need its own interpreter that is able to execute all the code in the isInstance or isSubclass overload method. So we chose not yet to go down that path. Future generations will get some PhDs out of that probably. But that would really not solve everything for protocols. It would certainly be a very large stick to kill that particular mouse. Poorly translated Dutch saying. Okay, well, glad you're all still with me here. So there are many details. I didn't even mention the typing module. You can look that up in the documentation. I do want to mention stub files and a thing called typeshed. Sometimes there is no source code to annotate. And where is mypy going to get its type definitions from? This happens when the code is written in C or C++ or Fortran. Sometimes there is source code, but it's too crusty or it's read-only. For some reason, you don't want to annotate it. The standard library has a lot of very crusty code that would not be easy to annotate. So mypy is actually configured not to bother reading the standard library. It never reads any standard library code, and it doesn't read any installed packet third-party code either. But it does read a thing called typeshed, which is a collection of stub modules that are basically class definitions with empty method bodies and function definitions and constant definitions and a few other things But like, it's syntactically valid Python code. It is not executable. But it has all the type annotations that are necessary to make mypy understand what's going on. And so we start out with like a stub for the built-ins module, and we have stubs for, I would say, at least a third of the standard library. That doesn't sound like much, but it's definitely the most popular third. And a small number of popular third-party code. And I think I already mentioned this. This is also an open source collection. It's on GitHub. And it's actually shared with all the other static type analyzers for Python. Another thing I want to mention briefly is, suppose you have 1 million lines of code, or maybe just 10,000 lines to start, small, somewhat small. How do you get that stuff annotated? If you point mypy at 10,000 lines of code that you wrote over the past 2 years, let alone 5 million lines of code you wrote over the past decade, it's gonna throw a lot of errors. It might even crash. Man, in 2015, when we started experimenting with that, we fixed a lot of mypy crashes. Just because the Dropbox code was much richer in all the corner cases of Python that it explored than any of the test cases we had thought of. At the last PyCon in May in Cleveland was a good talk by Greg Price. Clear code at scale, static types at Zulip and Dropbox, which sort of explains step by step how should you go about it. My 3-point summary of that is write some kind of wrapper script that sort of invokes mypy on the right set of files with the right set of flags. Start annotating only a small number of files. In fact, start analyzing only a small number of files at a time so you don't get overwhelmed. Set up continuous integration so that once you have a fixed point where you have 0 errors for at least the configuration that you actually have in that script, you will keep your developers or yourself, if it's just you, honest, and you don't introduce new type failures. And then I want to mention that there is a config file where you can set things like strict optional is true. The whole story I mentioned about optional actually only works if you use strict optional is true. You can also say disallow untyped calls, which is a useful flag that tells mypy, if I'm in type-checked code and I see a call to a method or function that has no annotations, flag that as an error. By default, when anything that's unannotated is just seen as a big blob of any's. And when you call that, it always type checks fine, and whatever it returns is now inferred as also having type any, and that in many cases sort of propagates through the rest of your code, or at least to the bottom of your function, or however far you're using the variable that captured that result. So by using disallow untyped calls, you can make mypy a bit pickier about that particular situation. There is like 30 more flags that affect all sorts of things like where to look for modules and a whole bunch more strictness flags. Oh yeah, there are also, you can specify most of the flags differently for different packages or modules. So here's a summary of the standardization effort. PEP 484 sort of was the result of a long and painful discussion in the community about, well, should we have type annotations? What should they look like? What should the syntax be? In the end, the sort of the mypy design mostly prevailed. It's definitely not a complete standard. You couldn't start implementing a type checker from just that specification and end up with a useful type checker. It would sort of report errors for most interesting Python programs. The variable annotation syntax was not in Python 3 when it was created, so we had a separate PEP for that, and it's only available in 3.6. Then protocols were their own PEP. We have another PEP that lets you publish stubs outside the typeshed collection, because while typeshed is a really handy way to bootstrap you, for third-party packages, it really doesn't scale to have everyone submit their stubs to typeshed. In fact, there are many third-party packages that are not very popular and commonly used and have conflicting names. So whose package ends up in typeshed? So the answer is neither, but each package can publish their stubs with their package or as a separate pip package. And then there is the first thing that came out of Facebook was forward references, which I didn't even mention here, but they are somewhat painful syntactically. And there's now a future import where you can avoid most of that pain. That's actually it, except for questions. I have a bunch of handy links. mypylang.org is really the only one you have to memorize because all the others are linked from there. Oh yeah, how to install it, pip3 install mypy. MyPy itself, of course, is a Python 3 program, even though it can analyze Python 2 code. And here are some more links to all the various bits of tooling that I could remember this afternoon, including Pyre, which is named PyreCheck on GitHub. We have two of everything, it seems. We have two different packages that do runtime type collection, which is something I didn't mention at all. But again, when you're annotating a large code base that is already working and you've got unit tests and everything, it would be nice if you could instrument your running program with something that observes every single function call and logs what are the types of the arguments. And, well, it turns out it's not a completely trivial problem. So Dropbox and Facebook came up with separate solutions. Type checkers galore. So, questions, heckling, selfie requests. Thanks, everyone. Yeah?
So I have two questions about generics. So what is the variance story? So is listed, what's listed, can I say listed to list object?
Couldn't cram that into a slide either. The variance story is that there is a way to say it's covariant, invariant, or contravariant in each type variable. You can have things that have multiple type variables, like dictionary is invariant in both of its type arguments. On the other hand, mapping, which is a read-only version of dictionary, is covariant in the value type.
And the second question is, can you do in the body of a generic method new t, so t parens?
No. That is definitely an issue. I refrained from showing a certain example because of that. Currently, it doesn't seem to be a big deal because in general, people have already solved this problem for untyped code, which is kind of a cop-out, but that's sort of realistically, that's where we are. We're mostly adding annotations to existing code, and like that stack example works just fine without ever being able to instantiate T, obviously. There are other examples where it's not so easy, like the summing example. would be nice if you could create a new T. But the problem is in Python, you can't always create a new instance of a class without knowing the signature of its constructor. So we really don't, I mean, Python just doesn't really lend itself to doing something like that.
Java has exactly the same limitation for exactly the same reason, and it's statically typed.
Yeah.
Whereas C# went to some lengths to let you annotate your constructor declarations to be to support new T, for instance.
Interesting. Okay.
So when I told my coworkers in research computing the talk I was at, the request was if you could help address some of the Anaconda tickets that we've got from end users. I'm not actually going to ask that. What I am going to ask is something I'm curious about. You mentioned typeshed and people wanting to add stuff to typeshed, which would certainly be convenient. I'm actually kind of curious, how many cases are there of things being removed from typeshed because the authors of the packages have added the typing information directly?
We have not done it for that reason. We have removed things from typeshed, but always for the reason that the module or the package turned out to be hopelessly dynamic, and someone had contributed partial stubs that caused more pain than being helpful. I expect that people will start sort of taking their own annotations in their own hands. The first example that will happen, I think, is the attr package, or attrs. I think you do import attr. It's very popular in certain circles. It turns out that attr is not easily typed using this type system. But mypy has a plugin mechanism, which is currently still very experimental, but someone contributed a plugin that lets you type classes created with the help of attr's decorators. Attr is incredibly dynamic. It's a class decorator and a bunch of things you put in the class, and suddenly the class has an automatically generated comparison, constructor, a bunch of other things, maybe pickle support, hashing. And because it's a class decorator that sort of just adds methods to the class, mypy has no hopes of understanding what's going on there. So when you instantiate an instance of those class, mypy is very sad. Or actually the user is very sad. So using the plugin, we basically special cased mypy so that it actually understands what that class decorator does in that particular case without having a whole interpreter for class decorators built into mypy. But one of the first bits of feedback we got was, well, attrs is evolving. There's attrs 1.7 and 1.8 and whatever comes next. And they're all different, and now we want to have different versions of the plugin. That will happen. There are a couple of other packages, for example, Django, where people are working on a set of stubs. And PEP 561 is coming just in time so that no Django stubs will ever have to be placed into typeshed because Django can just publish its own stubs. And of course, it can publish different versions of the stubs for different versions of Django, which is also the point. Sure, back to you. Well, okay, let's do someone different first.
Based on the answer to your last question, I'm guessing that mypy does not play well with meta classes.
It supports a tiny bit of meta class magic. Just enough to understand enums, I believe. But yeah.
As a sort of practical question, when dealing with structured or semi-structured data, like from database queries or JSON, do people typically annotate some sort of proxy object like an ORM or some like Marshmallow, those sorts of libraries, or how do you I'm sure Dropbox uses some of those things internally. Is that how they sort of approach that sort of thing?
Dropbox is trying to stay away from JSON, not always successfully. This explains why we have a protobuf it's not a plugin. Well, it's a plugin for the protobuf compiler, actually. We don't have a good strategy for JSON other than saying, well, you have to write a verifier, and the verifier should probably return objects of a sane class that can be fully typed. If you have a very basic JSON schema that isn't recursive, you can also use a thing called typeshed, which is a hack where you can tell mypy, well, here's a type, and it's just an alias for dict, but type check it as follows. It should only have these 5 keys. And for the first key, the type of the value is that. And for the second key, the type of the value is that, and so on. And you have to only index it with literals for the keys. And it turns out that there is a lot of sort of Perl code written in Python that uses this approach, and JSON often follows that pattern as well. But yeah, there are definitely some things that could be done better for JSON in particular.
For databases, can you fix the DB API to report more type information?
Well, the DB API is purely a runtime thing, so it's too late because all the type checking happens just by reading your source code. So for databases, we would probably have to have some other way where you somehow get the database engine to spit out the schema, and then you have a little translator that turns that schema into a set of class definitions that have annotations in them, and then you can use that.
I was sort of thinking more along the lines of not statically, but dynamically, maybe statically too for something like link, but just the DB API itself doesn't do a very good job at reporting consistent data types about queries that are returned, for example.
Yeah, I'm afraid that is really out of scope for this talk because I have no idea what you're talking about. Sorry. File a bug.
One more question, John.
Okay.
First off, thank you very much for the talk, and I'll admit I'm not a Python programmer, so I'm not qualified to ask this, but these are 2 philosophical questions. I was startled by one of your slides saying the advantages of a dynamically typed language include the fact that it's exciting, and it's not boring, and it's popular. And a language is a tool, a power tool. If Black & Decker made a chainsaw with no safety interlocks, they could say it was a real exciting chainsaw, but I don't think that's what they would be going for. So the first part of the question is that a product should be safe above all else. And in retrospect, do you think it was a mistake to not have this be strongly typed, or rather statically typed from the start?
That's I don't know. I use the anthropic principle for that. If I had created a statically typed language, I would have had to compete with C++ and Java, and I wouldn't be standing here.
And that was the second part of my question, which is that it doesn't matter how good it is if nobody uses it. This is a huge audience for this class, one of the best of the quarter.
Thank you.
And so from the opposite perspective, a product that's easy to use or easy to jump onto the bandwagon, that looks appealing, that's fun, that does have value because otherwise it might just founder. I don't know how to balance the philosophy of giving people what they want versus giving people what they need. Giving people what they want versus pushing on them some, raising their consciousness so that they ask for something better.
And what exactly is it that they need? I mean, I also created a language that, while being dynamically typed, was not easy to segfault. And apart from one corner of the standard library whose only goal it is to sort of unsafely hook into C, you cannot segfault Python easily from within itself. I mean, you'd have to basically rely on a bug in the interpreter.
In retrospect, might the language have been defined with the best of both, where the types were declared up front, but maybe one of your types was treat this as a dynamic type, such that in special cases, like calls to standard I/O or something,
Yeah, C# uses that approach. I gotta admit, I mean, there is something to say for that idea. In ABC, there were no visible type declarations, but ABC was statically typed. The language design had to compromise because there was a different operator for each type, basically. Like, there was no operator overloading because, like, plus meant that both the arguments were numbers, period. And then there was like runtime stuff where, oh, well, actually, we have different representations of numbers, like some are rationals and some are floats. And the floats have a bit whether they were exact or not or something. But, and then there was a separate level in ABC where suddenly everything was still dynamic because you could sort of edit your code, and the system as designed did not have a did not retype check every piece of code in existence when you change one function.
Java 1.0 was successful because it was lightly dynamically typed. True facts.
Again, thank you and congratulations on having this semester project.
Thank you.